I will now draw, let's try to remember what does linear means, guys. So I have x of n. What does linear means? If I have x1 of n, what do I get? y1 of n. Good. And now if I multiply x1 of n by alpha, yes. Now I have x2 of n, beta. Therefore now I will also have beta. And now of course the trick was to say that if this guy is sum, my x of n is nothing but alpha 1 x1 of n plus beta 2 x2 of n, then the output sums, correct? Now, what's so magical about this property? When the system is linear, the most important observation for linearity is I can break my signal from a very complicated signal composing of different small parts together and actually study how the system responds to individual small parts. Okay? That's the most critical part. Now, how can you break a signal up, guys? The most easy way. Okay, so now I'm going to draw for you a signal and I'm going to ask you to break it up. The signal x of n consists of some value here, some value here, and some value here. 0, 1, 2, and nothing else. Can? Okay? How can you break it up? What's the easiest way to break it up? If this is 1, this is 2, and this is minus 1. What's the easiest way, guys? The three delta functions. Good. So I'm going to break him up into the 3 deltas. So this guy would be 1 at time 0 plus who? At time 1, 2, and plus one more, guys. What? Can you help me, guys? At time what? 2. What is the value? So now, this 3 is equal to this. Agree? Now let's write the equation for each one of them. This is, in terms of delta, what is the function called? Delta n, right? Exactly delta n. Agree? Because delta n means a spike at time 0 with value 1 and nothing else in between. Okay? The second one, what is this? His name is 2 delta n minus 1. So he is a scaled by 2, delayed by 1. Scaled version of a delta. Okay? The last one, of course, minus 1 delta n minus 2. Very good. Now I'm going to make one more for you. How about this one? At time minus 1, I have 3. Okay? So you'll be plus what, guys? 0, 1, 2. This is minus 1, right? Okay? So this guy will be firing to 3, right? Can you see, guys? And his name is? His name? His name is 3 what? Delta? Yes. So that will confuse a lot of students. At that side is plus 1. At this side is minus 1. Okay? Okay? So what did I just do? I have decomposed a complicated signal into small parts. Right? And our system is linear. So now I want to see what happened here. This system H is LTI. And I want to see what. Okay? So what does linearity tells you, guys? I can study individual system. Yeah? And I already tell you When I send an impulse, I get an impulse response. Can? Okay? So now let's say impulse response is 1, 1. 2 ones. That's all. At time 0 and time 1. Nothing else. So this is called h of n. Can? H of n is nothing but these two guys sticking up. Pa. Okay? First question. Is the impulse response finite? Impulse response or infinite? Finite. Why? Because? No. No. Finite means because it dies. Is it absolutely summable? Yes, because it's nothing but 1 plus 1, 2. Is it stable? Yes, because it's absolutely summable. What is absolutely summable? The impulse response is absolutely summable. Okay? So everything is okay now. So this guy produces this guy. Come on, this guy will produce who? First, he's linear, right? Okay, then he's time invariant. Means today I send an impulse, tomorrow I send an impulse, same. Okay? So now I'm sending an impulse, one sample later, scaled by 2. What will I get, guys? I'll get time 0, time 1, time 2. If I have sent like this, it's simpler. I throw away the 2 first. What will I get, guys? 1, 1. At where? At 1. So it is 1, 1. Right? But now, what do I do? Yes, I scale by 2, right? So now it is, which is value 2 here. Can? So if upstairs is called Hn, what does this guy look like in terms of Hn? Come on. Ma'am? 2H. Very good. Now, I don't like to use the word 2, okay? Because 2 is a, yeah? I'd rather, let me call this is x what? X1, right? This guy? X2, right? This guy? X0. Agree? This guy? X of minus 1. Yeah? The value physically there. The absolute value. So this guy, 2, is what? X what? X? Who is he? Number 2 is X what? X1, right? Yes? X1. You will see a pattern very soon. Is X1 multiplied by Hn minus 1. You see a pattern? Okay, one more. Can? So now let's try the last one. This guy, okay? So let's ignore this again. Can? Then what will happen, guys? 0, 1, 2, 3. At where? Which point would it fire? At 1, at 2 and 3, right? Which property am I using here? Linear or time invariant? Sir, which property? Yes, time invariant, because I'm firing the impulse at sample 2. I want to, the impulse response is happening at sample 2. Yeah? And the shape looks exactly the same. It is the time invariant property I'm using. Can? Now I'm doing minus 1. Which property am I using? Which property? Yes, linear got 2 property. One is the homogeneity. One is the scaling. Yeah? Homogeneity is the scaling. One am additive, right? So which one? Yes, the scaling. So minus 1 times 2 guys shooting up makes the 2 guys shooting down at where? Here and here. Minus 1, right? So this one, if I have to write the equation, looks like h of n minus 2, right? Yes? Multiply by what? Multiply by minus 1, right? And who is minus 1? X what? 2. Can you see the pattern now? It's not a coincidence, huh? X1 generate Hn minus 1. X2 generate Hn minus 2. Okay? This guy? X0 generate Hn. So what is the pattern, guys? Okay. So I will jump to this figure. In this example, I send the impulse, I get some impulse response. I send a scaled delay impulse, I get the scaled delay impulse response. Right? And then what do? I sum all this to get my input. I sum all this to get my output. Right? That's what I'm trying to get. Huh? Now look at this equation. And can you see how did it become this equation? Because it is nothing but xk Hn minus k for all xk. Clear? And you just derive convolution equation from first principle.